It was very nice to sit here watching Graham and Gopan doing their presentation on St. John's. I would say that I was there for 4 to 5 days, and it took me 30 days of antibiotics to get rid of all the things I brought home with me from St. John's. Okay, are we ready? Lovely. So this is one that you wouldn't have heard before. This is a project that's only been announced about a month ago. FUNcube Lite is the latest project from AMSAT-UK. It's a fairly short duration project and it's running very, very quickly. If you are here because you think this is AMSAT-UK's first satellite to Jupiter, then sadly you are in the wrong place. This is definitely low Earth orbit, but there is some sort of logic to the naming of this satellite, which we'll go into. Okay, so we've got an opportunity to fly a payload on a 6U CubeSat from a group of universities. There is a collaboration between 4 universities in the south central part of the UK and a whole lot of industrial partners. The 4 universities in space south central are University of Surrey. We've got lots of good friends there and a history with that particular university, particularly the Space Centre. University of Portsmouth, University of Southampton, and another university who joined the group fairly recently, a University College in London. All have various departments doing space studies to varying degrees. Some are more focused on instrumentation rather than satellite missions, but all of them have decided to get together to try and promote space in terms of university studies, and have, I think it's about 170 different industrial partners, primarily across Surrey, Hampshire and the Isle of Wight. And when you look at those industries on a map, it really is very, very impressive, including people like SSTL, of course, who are a spin-off from University of Surrey some years ago, based in Guildford, Airbus, Kinetic, BAE Systems, and a whole host of other people that it was really good to see when I went through the listing. So Space South Central is essentially there to promote space studies and to liaise with industry to make sure the students are studying the right sort of things. 3 of those universities, Southampton, Portsmouth and Surrey, have got together to try and do some work on real space hardware, which is something that's actually quite difficult to do in the UK. As far as I'm aware, there have only been 2 satellites registered to universities in the last 35 years or something. The original UOSat series from Surrey back in the 1980s, and more recently a satellite project from the University of Manchester. Other than that, all of the things being produced here are collaborations with other countries. So it's very exciting to see these people finally getting some designs ready for their students to put into space. So where does this Jovian-1 come from? Well, the program that's been designed by the 3 universities has been called Jupiter. And if you have a look at this, it's the Joint Universities Program for in-orbit training, education and research. So a very, very nice acronym. The idea, of course, is to be able to give students a bit more of a practical experience in putting things together for space. The liaison with industry will help the UK space sector's growing demand for specialist skills, so hopefully they'll have an input in some of the course content. And as I say, 170 industrial partners across south central UK. This is hoped to be a rolling programme, and so if it's called the Jupiter programme, the first satellite in what will be a series is going to be called Jovian-1. So that's where the naming comes from. The press launch for this project was only the 20th of September, so what's that, about 3 weeks ago now. That's the press launch photo with students at Surrey University. And the first public glimpse of what this project is going to be about is this little representation of the satellite in the foreground there. A 6U CubeSat. And if you have a look at that, gravity is not working to the best effect there. Is a deployable solar panel, 3 sections, a total of about 900 millimeters long. So this is going to have a reasonable amount of power, which is quite good. Also on the front of this 3D printed representation, a couple of patches. As far as I understand, this is going to be working on S and X band, but the satellite will use commercial frequencies for all of its science payloads. So looking at the satellite first, and then we'll have a look at the FUNcube Lite payload in a few minutes. The satellite's a 6U satellite based on a structure and avionics from the Danish company GOMSpace. It's going to be 3-axis stabilized, so it should be able to track a position on the Earth quite nicely. It's got a single deployable solar panel, which will give it a total power budget, if all the cells are sort of pointing in the right direction, of 45 watts, which is an amazing budget for a CubeSat, which is very good to see. On board the satellite, there are 5 payloads, 4 from the universities and 1 from AMSAT-UK, which we've called FUNcube Lite. FUNcube Lite, primarily because this is a very short timelined project, so we've had to basically get things that we've used before, either use them directly or adapt them so that we can get this produced as quickly as possible. The bands in use for the satellite will be S-band. It has an omnidirectional transmitter. Well, omnidirectional is perhaps a little bit overstated, because with a structure that's 6U high, an omnidirectional antenna is going to suffer some blockage, but nevertheless an omnidirectional is there before it manages to get attitude control sorted out. It will have a command uplink on S-band and a downlink on that frequency. But it also has an X-band transmitter on board. So X-band in this case is 8 to 8.4 gigahertz in terms of an allocation. And it should be able to get its Earth observation data down quite quickly and effectively if it gets licensed on that band. From an AMSAT perspective, the entire satellite uses a CAN bus for communication. I think there's LVDS in there as well, but we're not associated with that one. So any communication we do is going to be CAN based. It's not something we've done before very much, so this is something that's going to be new for us, and he's certainly got a bit of head scratching to try and get around the various protocols that are in use within the CAN system. Very short project timeline. This whole thing started earlier in the year, around March or April. We've now got to a situation where all of that early preparatory work, which was essentially project planning and finance, has resulted in some orders being placed to GOMSpace and other suppliers. Hardware is due to be delivered in the next couple of weeks, which is very, very good. And for us, we've got to try and deliver working payloads, so flight model payloads, by somewhere between December this year and February 25. So we've made some progress, but really it's a huge effort to try and get things prototyped, tested, and then a flight model being produced, and also some environmental testing before that as well to make sure it all stays in one piece. So here's a CAD image of what they're doing down at the University of Surrey at the moment. The project is based at the University of Surrey. Essentially a 6U satellite, so this is, in terms of size, 10 centimeters across here, 20 centimeters in this dimension, so if you like 2 3U CubeSats side by side, and then 30 centimeters from top to bottom. At the top, this panel is in 3 sections. This solar panel just stows down this side, and when it's in space, that deploys, should all come out at 90 degrees. But the really nice thing about this is that at the central point on the solar panel, there's a mechanical connection, and that solar panel can rotate around one axis so that it has a degree of ability to follow the sun throughout the orbit. So if it works well, we should be able to get quite a decent amount of power from the system on the satellite. Just here on this face, this is the space-facing side of the satellite. The Earth is down in that direction, so Earth-facing is down there. There are patch antennas on the front of the satellite for S and X band. The S-band Omni is down here. I'm sure you can see that while it's Omni by name, there's an awful lot of structure behind that, but nevertheless, it should be quite useful. 38.4 kilobits a second is the maximum rate of the Omni. The X-band and S-band is much faster than that. In terms of AMSAT-UK, we're able to produce the circuit boards for the payload without any problem. But we needed antennas because with the existing antennas on the spacecraft, there was no UHF, no VHF antennas. So we've come up with a plan to fit an antenna deployer on the bottom. So if you imagine that facing the Earth, we've got a dipole with one element coming out of this side at the bottom of the spacecraft and the other one here. This element here is a 2-meter monopole. So what's that, about half a meter long, isn't it? So to give it some scale, we've got a satellite that's 30 centimeters and an antenna that's 50 centimeters long. So it's going to be quite interesting when it gets deployed. Hopefully that monopole will work okay, because with all of this other conductive metal work down here, it should give us a reasonable earth for the monopole to function against. So previously we've used dipoles, they're automatically very efficient, but this time we've got to work a monopole effectively against Earth. So this is going to be quite interesting. Power system, 3-section rotatable solar panel, as I've said, 200 millimeters by 900. If the panel is not deployed, there's a total of 38 solar cells visible to space. Once the solar panel goes out, that increases to 70. So even if something doesn't go right with the solar panel deploying, there's still enough power to run the mission, but perhaps not with everything functioning 100% of the time. Energy storage on board, it's 85 watt hours, which is fairly decent really for a CubeSat. Lithium-ion battery based. Nominal voltage 28, although the reality is I think something like 26 volts, discharged 33.2 I think is the fully charged voltage of the battery pack. So we've also got to regulate that down to what we would normally find on one of our payloads, which is about 9 volts. So Jovian-1 payloads from the students. We've got some imaging payloads taking still and video images. Obviously with the microwave downlinks they can get video down, so that's going to be very interesting for Earth observation. So all 3 universities taking part in that. From Southampton there's an intriguing dark matter detector. This is a technology demonstrator, sort of proof of concept. The dark matter detector actually has a laser system internally as part of the detection methodology. So although the laser is not exposed to space, we've still got to find the power to actually power that up. So it should be quite entertaining, and I'm sure it will be the subject of a few papers when the results of that finally come down to Earth and get written. Space radiation monitor, I think that's the physics department at University of Surrey. So they've got a radiation monitor that they've developed there that they want to demonstrate in space. University of Portsmouth have what I think we can probably think of as an AI payload, which is described as an innovative tiny machine learning payload. It essentially takes data from all of the other payloads on board and tries to analyze that, find patterns, predictions, and then sends those results down to the ground. And finally, FUNcube Lite, which is really, I guess, our main interest. Ground station for the satellite is going to be based at Surrey. If you go past the universities, you can see a number of dishes on the roof there. This one is 3 meters. It's 35 dBi on S-band with a beam width of 1.6 degrees. So that's going to be fun on the first pass where you don't really know where the satellite is. So yeah, trying to locate the satellite with that dish is going to be a challenge. And if it's that narrow on S-band, you can only imagine how narrow that beam is going to be on 8 gigs. That's going to be extremely tricky to find. I think in reality, there'll be another dish or a helix or something mounted on the side to act as a guide. So if they can find that signal with a fairly wider beam width antenna, see that on a display, then they should be able to, focus in with the big dish. Uplink for commands is in commercial S-band, which is 2025 megahertz up to 2120. Downlink 2200 to 2290 megahertz is the allocation, so it will be somewhere in there, frequencies to be determined. And equally, the X-band downlink is 8 to 8.4 gigahertz, and again, there'll have to be some negotiation on available bandwidth and frequency allocation there. As recently as last weekend, this was all upgraded because you can imagine tracking something in deep space on X-band, which is what this was used for up until recently, is fairly easy. Things tend to move fairly slowly when they're orbiting Mars, for example. Trying to track S and X-band in LEO, however, requires something that can move quite rapidly. So in the last few weeks, they've upgraded the rotator system here, and they've got a new dish feed that's going to be fitted shortly with selectable right-hand and left-hand circular polarization for both bands. Just taking a look at that, not up on the dish yet. This is the dual band dish feed with the mount on the left-hand side, if I can find the laser. This is effectively an 8 gigahertz circular waveguide in the middle with the 2 gigahertz circular waveguide around the outside of that. Connectors on the bottom feed into the 8 gigahertz, and then you can just about see some holes drilled in the side of the waveguide there, ready for the probes to go on for the 2 gigs. So that's still being assembled. I think it's being manufactured in Holland, and that'll be mounted on the dish using these rods, 4 of those around the base of the structure. So it can be mounted up on the dish at Surrey for getting signals on those 2 bands. So having looked at the Jovian-1 satellite and their plans for it, let's have a look at the FUNcube Lite payload. Well, most of this will be fairly well known to us because this is, as I say, a very short duration project. Hardware delivery from us, December to February. And then I've seen charts that say environmental testing, vibration, thermal vacuum, fairly soon after that. And really, with any of these projects that's being funded by a university, finding the funds for the satellite is one thing, but when you're employing a group of specialists, at some point that money is only budgeted to a particular date in the diary. So one of the things about this short-term project is that if you overrun it, you then don't have any money to pay the specialists. So the timeline here, I think, is going to be kept to in a very short margin. So FUNcube Lite then, communications system payload providing BPSK telemetry, as we know and love from our various other missions. It will include, I think, 12 channels from our payload itself, but we'll also be picking up a lot of data from Jovian-1, including GPS data. So for the first time, we'll get data down via our telemetry to tell us whereabouts above the Earth the satellite is. And so that will be a first for us. We're incorporating a single channel FM voice transponder or repeater for amateur radio use. It will be UHF uplink, VHF downlink, and will have 67 Hz CTCSS as standard. The BPSK telemetry and the FM downlink will both use the same frequency, which means that when we have the payload running, it will either be telemetry or it will be in sort of voice repeater mode. So we can't run both of those at the same time. Power saving modes, of course. CubeSats are infamous for being under budget in terms of power. So we've always incorporated lots of different ways of running our payload by being able to adjust the power, being able to adjust the amount of time it comes on. We can switch it on and off when it enters eclipse, for example, to save power. So there's lots of ways there that should guarantee that no matter what the power budget is on the main satellite, there's still enough power to run our payload, which is good. Manual mode change can be done via a UHF uplink, so we have to be able to command it legally anyway to be able to turn it on and off. But as I say, it can change modes on eclipse entry and exit if we need to. We're using flight-proven hardware where we can, either directly by taking a design that we've already got and using that, or by taking small modifications to existing hardware in some cases. So we're taking elements of hardware used on FUNcube-1, JY1-SAT, and the SAO missions. And also, of course, we've got the Windows-based ground station software, which will decode all the telemetry as it comes down, and an online data warehouse to store all the data, which was particularly interesting to University of Surrey because, of course, they can have students in future years do analysis on data that we've collected. So that should be good for everybody, I think. So moving on the right-hand side is one of our earlier projects, but the purpose of it here is just to show the construction. We are using a 4-board solution based on PC104 CubeSat format, so stacked with supporting rods. So we have a standard size printed circuit board with 4 rods in the corner, all held together with spacers and headers that interlock. So that isn't the format being used for the student payloads. The student payloads are using a more conventional for space tray assembly. So all of their modules will be built into trays that can be plugged in and out. But because of the time pressures, we're going for this format. The stack height will ultimately be about half a U or thereabouts. So about half the size of a 1U CubeSat, but mounted inside. And if we have a look through there at the 4 boards, we've got a VHF UHF communications board, 435090, I think is the frequency we're going to apply for. We have a VHF power amplifier with an FM transmitter mounted on it this time. So the amplifier has flown before, but we've added FM transmit capability. Command, control and telemetry, which is something that we've used on previous missions and is fairly well proven with a lot of flight heritage. And finally, something which we've called Cannibal. I think the author of that name standing at the back somewhere. Cannibal is the CAN interface board for AMSAT Lite. Well, you've got to have some fun somewhere, haven't you? That board will carry a CAN interface to the rest of the satellite. Because we had space on that board, we've decided to pop a radiation sensor of our own on it and the switch mode power supply that's necessary to take the 28 volts down to 9 volts for our mission. We also need, though, the antenna deployment system, and no one in AMSAT-UK has the experience to put one of those together. And the reason is these things are really mechanically based. So we've turned to some old friends, Isospace in the Netherlands. One of their best-selling products is their antenna deployment systems for CubeSats. On the right-hand side, we've got an example of that we've flown on all of our missions that have been CubeSat-based. You can see it deploys 4 elements in standard format. So on this one here, you might have a 70 SEMS dipole across these 2 elements. And then vertically here, in previous missions, we've had 2 meter dipoles fitted like this. Internally, this is a CAD image, which is available on their website. It is a true mechanical work of genius. I mean, for this thing to be so reliable, it is amazing. And internally, we stood no chance of producing something anywhere near the reliability of this product in the short timeline. So we've just taken a dip into members' funds and we've splashed out some money. And this is on a bit of a lead time, but nevertheless, it's been ordered for this mission. So the FUNcube Lite satellite, if you like, block diagram or system connection diagram looks something like this. Top left-hand side, we've got that Isospace antenna deployment system with its UHF and VHF antenna. Immediately beneath that, we've got the transponder board, which is essentially a UHF receiver, the telemetry generation, and the repeater logic and timers. To the right of that, we've got the CCT board, which does all of the command, control, and telemetry. We'll have a look at each of these in a minute. The RF power amplifier is above. That's something like 29 dB gain and about 600 milliwatts out. And then on the right-hand side, we've got the Cannibal CAN interface board, and importantly, a harness connector to the rest of the satellite with power supply lines coming in, CAN coming into it, and a loop through with CAN coming out. So quickly through these pictures I think have been used before. This is the command, control, and telemetry board. It's based around 2 pieces of semiconductor. First of all, a Xilinx CPLD, which acts as a command decoder, and also it formats the modulation for the telemetry. This is a particularly reliable system because the other piece is a microcontroller from Freescale. Microcontrollers have been known to fail in space before, but this Xilinx firmware, if you like, has been ultimately reliable. And even if the microprocessor fails, it still means that we can control the mode selections on the satellite. So we can have complete microprocessor failure, but we've still got direct access to being able to switch modes by using this type of topology. If you've got any questions on any of this, Duncan is standing at the back, and I'm sure he can answer questions later if you want. The first version of this was launched in 2013 on AO73. It's still working 11 years later through some pretty amazing solar activity at the moment at 600 kilometers and hasn't failed. A little bit of an internal diagram here. I'll try and speed up a little. The internal diagram of the CCT board is there with the Xilinx CPLD at the top and the processor underneath. Only an 8-bit processor, but we are very, very mean with power on this. So if we can do it in a simple format with minimal power, then that's what we choose to do. The telemetry coming down, this is, I think, from AO73. It's a mixture of whole orbit, real time. I think we've had high resolution data on this one, which is once a second. And we've previously used FITA messages, so little text messages for school outreach, where we can upload a text message and schools can download that and their students can go, hey, that's my name coming down from space. That's pretty amazing. I think we had 9 or so for AO73. We'll probably cut that back a little now because we've got other data from the satellite that we would want to include. PA board, loosely based on our previous missions, upgraded to include a driver. Also, we've included a combiner on the input. So with this board, we can have input signals from various sources on board a satellite and just combine them and then amplify them and transmit it out. It's a Mitsubishi amplifier, an FET. It's got 4 channels of telemetry on board, and basically I think we worked out this has spent 25 years in space, this particular PA design, without a failure on several different missions, obviously. On the bottom side of that, we've just adapted it. This is the entire FM circuit here. That's an entire FM transmitter. We sort of thought we'd go for the easy solution here, the minimal component count. The FM transmitter is just one chip. Silicon Labs SI550, which is a voltage-controlled crystal oscillator. So the idea is we should be able to apply a control voltage to it, and it frequency modulates it. That seems to work very nicely. The other components here are just basically a low-pass filter to get rid of some of that high-frequency hiss that would otherwise cause the bandwidth to be quite wide. Does it work? Yeah, we've done a linearity check on the engineering model. Nice and linear up to 500 milliwatts. We've pushed that a little bit since then, so it goes to over 600. For VHF, that's perfectly okay. FM transmitter testing, we need to test this stuff on the ground first. We needed to set the deviation. We chose 3 kilohertz as a reasonable figure. Deviation meters aren't terribly reliable, and I don't have one anyway, so we had to find another way of doing it. We found a method used to assess deviation by nulling the carrier. So when you transmit a carrier, you get a single frequency. If you apply FM and you turn the volume up with an audio tone going in, you can calculate an audio frequency where you turn up the deviation, the power of the carrier just disappears down or is a null. And that's an extremely accurate method of measuring deviation. So we went for this technique. FUNcube Lite telemetry, I think we've looked at this on many other occasions. So 1200 bits per second BPSK, 24 5-second frames to get all the telemetry down over a 2-minute period. Real-time, whole orbit and text messages. We've also got a little bit of expanded memory capacity on this, and as there is an imaging payload on board, we've yet to talk to the students doing that, but they've expressed interest in that, well, if their payload doesn't work entirely as planned, we might be able to grab small resolution, low resolution images and transmit that down as part of the telemetry on board FUNcube Lite. VHF comms, as I say, UHF receiver in the middle, providing command audio, and up at the top here, we'll route the audio in this direction for the transponder function. 8 channels of telemetry available from a Maxim chip, which gives us 12 overall, and the baseband telemetry is also modulated on this board, and it gives a low-level output going to the PA. So that's essentially how it operates. Loosely based on these 2 boards, half of the board at the top, which comes from the ISAO mission, and about 1/3 of the board from the bottom. So it's a bit of a mishmash there. We certainly can't use these boards as they are, but we can take elements that we know work, combine those, and with a bit of luck, that should be what we're flying on ISAO in a much modified form. Cannibal, the CAN interface. Again, Duncan's in charge of this one, so any questions on CAN, or perhaps we can ask you some questions because we're still very much learning. A PIC processor with a CAN interface on it, CAN transceiver to interface to the satellite bus. We've added a BG51 radiation sensor, which is an array of pin diodes to detect beta, gamma, and X-ray. The radiation detector is this one at the top. It's just a 3-terminal device. It takes 25 microamps, I believe, at 5 volts. So almost any CubeSat can fly one of these without any effect on the power budget. We've tested it at a local school with some gamma and beta sources. Appears to work very well. So that should be incorporated as well. Okay, so coming towards the end now, and there's a lot of questions that have remained unanswered so far. Jovian-1, we know it's under construction, we know it's financed. When is the launch date? Who's the launch provider? Whose rocket are we going to bolt this thing to? Where's the launch site? Will we be able to go and drive and see it, for example? What's the altitude in orbit to give us an idea of where this thing is going to enable us to communicate? The inclination of the orbit, we'll be able to hear it up in Scandinavia. The lifetime of the satellite, think of that huge solar panel hanging out. That's going to have a lot of drag. That's going to be an interesting one. And of course, the concept of operations, how much time will the payload actually be on? Sorry. Yeah, all of this stuff, to be fair, we don't know much about it anyway, but we can't say because there's a non-disclosure agreement in place. What I would say, though, is this project is very fast moving. And if they're going to meet the budget, then all of these things have to be sorted out fairly quickly. So I think we can anticipate there are going to be announcements on all of these topics in the short term rather than medium or long term. So we'll just have to look out for those when they actually happen. Which leaves us 5 minutes for any questions, as long as it's none of these. I think there's a microphone around somewhere.
Thank you, I've got one.
Oh, well done.
The age-old question, CTCSS, why have we incorporated that? Because obviously you want to use some digital modes, which we've done before on D-Star and such. It's a bit of an inhibitor.
It is, but bearing in mind this is an FM receiver and an FM transmitter, you have to sort of limit it somewhere, and you can't run it completely open because of the effect on the power budget. It's just what we felt we could do in a short period of time without perhaps realizing the potential of other types of modes. So if you'd like to have a chat with us about other types of modes, there's plenty of bar time and coffee time left. I'd be very pleased to talk to you about that. Dinner, okay, well done, got your ticket. Any other questions? Okay, got another 2 here. Is there a microphone just behind you, Dave?
Thanks very much. Yeah, hi, thanks. Yeah. Probably a very basic question, which everybody else knows the answer to. Apologise. You were saying this, the satellite has got an Earth-facing side,
yes,
and a space-facing side. How do you maintain that orientation? Because I was thinking drag on the solar panels might well cause it to rotate.
Yeah, indeed. The traditional way of doing that, of course, well, the need for that is if you've got a camera on board, you want the camera to point into the right place. So you must have the ability to point the camera at the object you want to photograph. Equally, if you've got microwave patch antennas, they have a fairly wide beam width, but again, you've got to make sure it's Earth pointing to get that antenna pointing in the right direction. The answer is you're in low Earth orbit, so there's a magnetic field. So if you have something called magnetorquer rods, you can pulse current through them, and they exert a force on the satellite. So they move the satellite by magnetic interaction with the Earth's magnetic field. There's also, what do they call the wheels? Momentum wheels? Reaction wheels, and that gives it a much more smooth slew. So if you're taking a photograph in one position, as the satellite's traveling at 7.6 kilometers a second in orbit, you perhaps need the camera pointing at an object over several seconds to get the image you want. So there are a couple of different methods of attitude control on the satellite. But you're right, that solar panel's enormous, isn't it? Any other questions? I saw one over here.
Yeah, so the question was pretty much about the same, yeah, about stabilization. So, but all the ways you mentioned, they're quite power hungry, let's say. Yeah, and because you need to rotate the satellite quite often, yeah, because it's a low orbit one. So the question is, was it used on the previous flights or not? I mean, such kind of idea.
Yeah, I mean, this is a standard method on most satellites. Actually.
Yeah,
most
but for small satellites, was it used
yeah,
before?
in fact, on one of our missions, JY-1SAT, which is obviously owned by Jordan, but nevertheless has a FUNcube payload on board, there's a small board on there which has smaller versions of torque rods and coils on board, and that has the function of stabilizing the satellite, because sometimes when they're ejected from pods on the host rocket, they can come out tumbling, and the important thing there for communications is to get the things stable so that they're not rotating out of control. So yes, it has been tried, and if you get the software right, it works really well.
Okay, thank you.
Okay.
Hello, you mentioned a protocol to get telemetry. What about images? So will they be publicly available?
I think the students will want to see, and certainly remember that one of the objectives of this whole project is to make potential students aware of space studies. So if you want to attract students into your university, I can't imagine why you would take a photograph and not publish it. So I would think there's going to be a lot of these photographs published coming down on S and X band. If we get to send anything down, it will be lower resolution because our data rate is very slow in comparison with those other bands. But if we can do that, it will be an interesting thing to do. We have sent down still images before on JY-1SAT, some lovely pictures that were preloaded. So we know we can do it at this data rate. It's just a question of who formats the image, which might be several megabytes, into something smaller and then transfers it to us. So yeah, in discussion.
Thank you.
Okay.
And actually, while we're talking of software, do you have any facilities for changing firmware in flight, or is it all baked in on the ground?
I would have to say baked in on the ground, as I look to my software developing colleague at the back, who's shaking his head. He's the one to talk to later if you've got plenty of software questions. But no, we program this on the ground. And then after that, it's just a question of executing whatever we've managed to program in it. Hopefully, we think of all the scenarios. Sometimes we don't, but we're left with whatever there is on the satellite. But hopefully, by the time we're here next year, this will have progressed a very long way from today's brief chat. Thank you, Dave.
Thank you, David. And I'd like to thank him, please. I'd like to say something as well about FUNcube Lite. Dave keeps saying we. The we is the FUNcube team, and to whom we are very, very grateful. FUNcube 1 has been 11 years old, and that's a measure of how good the design was, and the same thing is going to go into this as well. My other comment is, David also mentioned that we'd be talking about collecting data in the data warehouse. When we started out, we had about 2,000 people collecting that data. As things have changed, that's dropped, of course. So this is another opportunity for people out there to actually feed us more data into the warehouse. Thank you. And from my point of view now, it's a break for lunchtime. We resume here at 1:45. Thank you very much indeed.